$13.3 billion. That is the price tag of a single USS Gerald R. Ford. To the casual observer, it is a floating airfield. To a naval strategist, it is the most complex piece of sovereign territory ever engineered. For 7 decades, the United States Navy relied on the Nimitz class, a design powered by steam and brute hydraulic force. But the limits of steam have been reached. The Ford class represents a total departure from 20th century physics. It isn't just a ship. It is a floating power plant capable of generating 104 megawatts of electricity, enough to power 60,000 homes. But why invest the GDP of a small nation into a single hull? The answer lies in the sortie generation rate. In modern warfare, the winner isn't the one with the most planes. It's the one who can launch, recover, and rearm those planes the fastest. Today, that we go inside the steel. We examine the electromagnetic railgun technology launching 30-ton jets, the nuclear heart that won't need refueling for 25 years, and the strategic reality of why the supercarrier remains the ultimate chess piece in global projection, even in an age of hypersonic missiles. The A-1B nuclear reactor. Inside the hull of the Gerald R. Ford lies a generational leap in nuclear engineering, the Bechtel A-1B reactor. Unlike the previous Nimitz class, which relied on the A-4W, the A-1B produces 3 times the electrical power. We are moving from a ship that uses steam to move valves to a ship that is essentially a massive floating capacitor. This shift was mandatory. Modern directed energy weapons, high-powered radar, and electromagnetic launchers require instantaneous surges of electricity that would have melted the wiring of a 20th century carrier. The A-1B is designed for a 50-year service life without a single midlife refueling, a feat of metallurgy and core design that remains one of the most closely guarded secrets in the Department of Defense. Electromagnetic Aircraft Launch System. For 70 years, the snap of a steam catapult was the heartbeat of naval aviation. But steam is linear. It hits the aircraft with a violent, fixed jolt that stresses the airframe. The emails replaces pistons and pipes with a 300-foot linear induction motor. By using electromagnetic pulses, the system can fine-tune the acceleration curve for a 4,000-pound drone or a 70,000-pound, fully loaded F-35C. This precision reduces structural fatigue, potentially adding years to the lifespan of the air wing. More importantly, it recharges in seconds, not minutes, removing the recovery time required for steam pressure to build back up. The pit stop deck layout. The Ford-class deck is designed around a single metric, SGR, sortie generation rate. On a Nimitz carrier, aircraft movements were a ballet of chaos. On the Ford, the island has been moved aft and reduced in size, creating a massive centralized pit stop area. Aircraft no longer have to cross the landing strip to be refueled or rearmed. The goal is a 33% increase in flight operations, aiming for 160 sorties per day in sustained operations and up to 270 in high-intensity surge conditions. It is the difference between a carrier that defends a region and a carrier that dominates an entire theater of war. So turboelectric recovery. Recovering a jet is essentially a controlled crash. The new Advanced Arresting Gear, AAG, replaces the massive hydraulic water brakes of the past with rotary hydrodynamic energy absorbers coupled with electric motors. The AAG system uses energy-absorbing software to calculate the exact weight and speed of the incoming plane in milliseconds. If the jet is off-center or too fast, the system adjusts the tension on the wire instantly to prevent a bolter or a catastrophic cable snap. It is a digital solution to a high-speed mechanical problem. The phased array shield. The most striking visual change is the island. It is smaller, stealthier, and houses the dual-band radar, DBR. By combining X-band and S-band frequencies into a single system, the Ford eliminates the need for rotating dishes. This phased array system can track high-altitude threats, sea-skimming missiles, and even small surface craft simultaneously without ever losing a lock. It operates with no moving parts, reducing the maintenance man-hours required by a factor of 10 compared to legacy radar systems. Automation and the human element. A $13 billion ship is only sustainable if you can afford to man it. The Ford was built to operate with 600 fewer sailors than its predecessor. This is achieved through Advanced Weapons Elevators, AWE, which use linear motors instead of cables to move ordnance from the deep magazines to the flight deck at double the speed. Every system, from the automated galley to the self-monitoring electrical grid, is designed to reduce touch labor. Over the 50-year life of the ship, and these personnel reductions are projected to save the U.S. Navy over $4 billion in operating costs per vessel. Strategic projection in 2075 critics point to the rise of carrier-killer anti-ship ballistic missiles, ASBMs, as the end of the carrier era. However, the Ford class is built with flexible infrastructure. Its internal compartments use modular wiring and open architecture software, meaning it can be gutted and upgraded as laser defense technology and autonomous swarm drones become the primary tools of war. It is a $13 billion investment not just in today's hardware, but in a hull that is expected to be the flagship of a strike group in the year 2070. If you're enjoying this deep dive into military technology, consider subscribing to the channel. And before we continue, I leave a comment telling us which country you're watching from. It's fascinating to see how these machines capture attention from people all over the world. The true breakthrough of the Gerald R. Ford is not any single weapon, but its total ship computing environment. This is the first carrier where the ship itself is an integrated network. The reactor, the catapults, the radar, and the elevators talk to each other in real time. When a jet enters the landing pattern, the radar informs the arresting gear. When the elevators draw power, the reactors compensate before the load even hits the grid. This level of systemic integration is what allows a 100,000-ton mountain of steel to react with the agility of a fighter jet. The Gerald R. Ford is more than a symbol of naval power. It is the most expensive and complex gamble in engineering history. From its electromagnetic heart to its automated vanes, every inch of this vessel is designed to ensure that the concept of the supercarrier remains viable for another half-century. Machines like this continue to redefine the balance of power in modern defense strategy. The story doesn't end here. Tell us in the comments. Which military machine should we explore next? Fighter jets, submarines, aircraft carriers, or secret military bases? And don't forget to tell us which country you're watching from.